Today we will continue with stereochemistry. In stereochemistry, we have done till now isomerism, then types of isomerism, that is structural and stereoisomerism. Under the stereoisomerism, we have done geometrical isomerism, and then we are doing optical isomerism. We know that till now that all the optically active molecules or object are chiral and they exhibit enantiomerism. A chiral molecule is that which cannot be superimposed on its mirror image, and both the non-superimposable isomers are called enantiomers. This we can see in the figure, that is, and this first diagram is showing hand, the mirror image of hand. These two mirror image and the object images are not superimposable, that is, these two are the non-superimposable mirror images of each other. Similarly, this is a tetrahedral molecule, and this model, ball and stick model of tetrahedral chiral carbon and its mirror image, these two are non-superimposable. So any optically active compounds are non-superimposable mirror of each others, and we can say that there are simple elements of symmetry which are used to identify whether molecule is chiral or not, that is, whether its image and object will be superimposable mirror images of each other or not. And for that there are some elements of symmetry which are generally categorized as follows, that is, simple axis of symmetry, which is denoted by Cn, then plane of symmetry sigma, then center of symmetry Ci, and then alternating axis of symmetry Sn. That is, these elements of symmetry are the simple tools to identify whether a molecule is a chiral or not, and the necessary condition for optically active molecule is to be chiral, that is, molecule should not possess any kind of symmetry elements, and the main symmetry elements which we generally use or see are these four. So we first define these elements of symmetry one by one, and then we reach to the conclusion, that is, first is simple axis of symmetry Cn. When a rotation of 360 degree around the axis of a molecule or object is applied and the molecule is rotated, thus obtained is not differentiable from the original, then the molecule or object is known to have a simple axis of symmetry. It is represented by Cn. That is, when a rotation is done by 360 degree, how many times the same identical image appears, that is the simple axis of symmetry. Example, in a water, it has a C2 two-fold axis of symmetry, that is, same position is repeated twice when molecule is rotated by 360 degree. And chloroform has a C3 axis of symmetry, that is, when it is rotated by 360 degree, the same position of atoms appear thrice, that is, we can see this is a water molecule, oxygen, then hydrogens. When it is rotated about this axis, then this position will appear twice. And similarly in this is the center of axis. When it is rotated, this position of atoms will be repeated thrice. So it has a threefold of symmetry. And from the above example, we can understand that if we rotate the water molecule by 180 degree along its molecular axis, we get the identical form of water molecule. Hence, water molecule has two-fold of symmetry. Similarly, if we rotate the chloroform molecule by 120 degree along its molecular axis, we will get the identical form of chloroform molecule thrice. that is, it has a threefold of symmetry. So this is the first element of symmetry, that is simple axis of symmetry, whether it is twofold, threefold, fourfold, or etc. So next is plane of symmetry, that is a plane which divides the molecule into two equal halves is called plane of symmetry. So when a plane that divides a molecule or object into two equal halves which are related to each other as object and mirror image, then that plane is called plane of symmetry. It is represented by sigma. Now we can see in this example, it is tartaric acid. In this carbon is chiral because it has four different groups attached to it. 1, 2, 3 and 4th is this group. Similarly, this carbon is also chiral atom because the four groups attached to it are different. 1, 2, 3 and 4th is this. So these two carbons are chiral, but it has this plane of symmetry which divides this molecule into two equal halves. So it is optically inactive. So it has a plane of symmetry from which we can say that it is a optically inactive molecule. And similarly, or we can show this by different colors. Here this has shown by red color, this by blue. That is, if this is real object and its mirror image, then this divides the molecule into two equal halves. It is divides the molecule into two equal halves. So it is a center of plane of symmetry. So next is element is center of symmetry, Ci. Center of symmetry is a point in a molecule from where if we move to the opposite directions, then at equal distance we get same atoms. That is, if this molecule, this is the center, if we move towards this direction, then Cl is present. At equal distance, if we move in the opposite direction, we must get this atom. So this is the center of symmetry. Similarly, if we move to this direction, it has Br atom. At the same distance in the opposite direction, again it has Br atom. So this is the center of symmetry. So a molecule has a center of symmetry when for any atom in a molecule an identical atom exists diametrically opposite at this point center and at equal distance from it, as in this example. So next is alternating axis of symmetry. An alternate axis of symmetry is when a molecule is rotated by 360 degree about its axis and then a reflected plane is placed exactly at perpendicular to the axis, and the reflection of the molecule thus obtained is identical to the original. It is represented by Sn. That is it. We can see in this example. In this example, that is 1,3-dichloro 2,4-dibromocyclobutane. It has a twofold axis, alternate axis. That is, if this molecule is rotated by 180 degree rotation about axis, then we get this placement of atoms. That is, this carbon will rotate to this position, that is this 180 degree, and this carbon, or say this, will move to opposite end, that is this position. So the molecule has been rotated by 180 degree, and the same, that is, if this is rotated by 180 degree, we get this. If we rotate this by 180 degree, then this is the same as the first. So when two rotations are done, we get the same molecule. That is, we can say it is a mirror plane perpendicular to axis of rotation, and this is the mirror plane. and so it has a alternating axis of symmetry, twofold axis of symmetry. So this is how the elements of symmetry are defined. That is, first is simple axis of symmetry, second is plane of symmetry, third is center of symmetry, and fourth is alternate axis of symmetry. So next is, what is chirality? What are enantiomers? Till now we know that chirality is a necessary condition for a molecule. That is, a molecule should not have any kind of symmetry elements present in it, and molecule should be dissymmetric, should not have any elements of symmetry, and or in the other words we can say that it must be dissymmetric, and such molecules are chiral molecules, and the property is called chirality. So the optically active chiral molecules which are non-superimposable on their mirror images are called enantiomers, and the process is called enantiomerism. And the molecule which shows enantiomerism should have at least one asymmetric carbon atom, that is, one carbon atom which has 4 different groups, one carbon atom which has 4 different groups or atoms around it. That this is the necessary condition for a molecule to be optically active. As we can see in this example, these are left hand, right hand, and this cannot be superimposed on each other, so these are non-superimposable, and chirality is the necessary and sufficient condition for the existence of enantiomers. But if we see in this example, tartaric acid, in this 2 asymmetric carbons are present. This carbon is asymmetric, 4 different groups are attached. One group is this, one group, second is group this, then OH, and fourth group is this, whole this group is fourth group. Similarly, this carbon is again asymmetric because it has also 4 different groups, one this, second, then third, and fourth is this group. So these both carbons are asymmetric, both have 4 different groups attached to them, but they have plane of symmetry. They can be divided into 2 equal halves. So it is optically inactive. Now this has the structure which just can be divided into 2 equal halves. Now its mirror image is this. Mirror image is again can be divided into 2 equal halves, so both are optically inactive. So both are the non-superimposable mirror images of each other. But if the element of these groups is different, that is, in this OH group is on the left side, in this it is on the right side, then now this molecule has no plane of symmetry, so this will be mirror images of each other, and these will not be superimposable on each other, so these are the enantiomers. So enantiomers are the non-superimposable mirror images of each other, and these are the optically active molecules. So next is, what is stereogenic center? As we have already explained, stereogenic center means a center which have 4 different groups attached, that is carbon, or we can say stereogenic carbon which has 4 different groups attached to it. So one carbon atom which is directly bonded to 4 different groups or atoms, and a molecule which do not have any kind of symmetry element present in it, such molecule is called asymmetric or chiral molecule. And all the chiral centers are stereogenic, but all the stereogenic centers are not chiral centers, and this can be explained in the above example also in tartaric acid. So in this example we can see that Bromo, chloro, fluoro, idomethane exhibits chiral carbon center, that is this carbon has 4 different groups attached to it, and we can see this, and these are the non-superimposable, and these are the optically active. So what is optically active? What is optical activity? Optical activity is the molecule which is optically inactive or which can rotate the plane polarized light. So the property due to which it can rotate the plane polarized light, that is called optical activity. So optical activity is the property of a molecule. It is a property of a molecule, or we can say it is the ability of a molecule, to rotate the plane of plane polarized light either towards left or right direction, is called optical activity. Optical definition of optical activity is very important, and as we have already done, it can be measured by a instrument called polarimeter. And this is also we have done this specific rotation we can calculate by this formula, where the each term has its own meaning. And now the enantiomers always exist in pairs, that is, one it rotates the light in right direction, other will rotate in the left direction, and these are the non-superimposable mirror images to each other. This also we have done. And then they have same physical properties like boiling point, melting point, solubility, density, viscosity, etc., and the chemical properties in a chiral environment. They have same physical properties and chemical properties. Now they have opposite behavior with respect to plane polarized light. This we know that if one rotates the light to the right, then the other will rotate the plane polarized light towards the left, and each isomer shows the same chemical reactivity with a chiral reagent, and they have different biological properties. That is, if example is when we grow penicillium glycom in tartaric acid, it consumes the one isomer and leaves the other. So biological activity of enantiomers is different. And then as if we take up for example glyceraldehyde, which is a chiral molecule, and due to a chiral molecule it has a pair of enantiomers, and which have the same physical properties, and they have different action towards plane polarized light, and we can draw its structure. So you have to draw its structure and then write its pair of enantiomers, which we will discuss in the next lecture. So thank you.